Welcome everyone, I'm J Wildberger, and we are discussing elementary mathematics for K-6 students. And in today's video, we are going to be looking at puzzles. So up till now in the course, we've been doing some very basic arithmetic, concentrating on addition and multiplication with a very geometrical orientation at first. And then we've moved on to having some practice involving some measurements. For example, lengths, weights, volumes, capacities, and areas. So today it's time to expand and have some fun with some puzzles. Puzzles that strengthen and entice students towards developing further their arithmetical skills, just at this very basic level involving addition and multiplication. Now, our orientation towards problems is that, first of all, they should be immediately interesting. There should be something about them that sparks a little bit of anticipation, a little bit of motivation towards what's going on here. The level of a puzzle should be suited towards the age and the ability of the student. So we want to have a puzzle with difficulty level enough that the student is challenged, but that they're still able to hopefully make some progress or solve the problem. To make that easier, we need to be a little bit flexible, and so we can think about a puzzle as not being a fixed kind of thing, but as having different aspects. Maybe there are more elementary aspects or elementary versions of a problem or a puzzle, and then there are more advanced aspects or examples. And so you have to maybe choose the right level of the puzzle for your child. Hints are important. So if the child is making progress but they haven't quite gotten there, it's nice to have a hint to give them a little bit further boost, give them some orientation to which way to go. Students should learn to work out simple cases. That's an important kind of orientation towards problems. We don't know what to do. Let's work out a simple case, okay, and see what happens in this simple case. And maybe after we've done that, maybe there's a second simple case that we can work out, and maybe a third. Then we can perhaps even start seeing a pattern in what's going on, and that will give us some insight into the more general situation. So we're looking for patterns is an important part of solving problems, something that we want to encourage students to start doing. And students should earn some praise. If they have a nice solution, praise them and congratulate them for their efforts. Now I'm touching base here with an interesting discussion that actually is important much more generally across mathematics education, okay? Not just for young children, but even into the university levels and beyond, which is that it's all well and good to have good explanations in terms of lectures, written materials, or videos. But that almost always needs to be complemented by a rich and representative set of problems and questions for the learner to practice what they are absorbing. Okay? So there has to be this balance between sort of theoretical understanding and actual doing, working things out. And in many online mathematics courses or MOOCs, there is really a very significant danger of concentrating too much on the lecture aspect and not enough work is put into creating rich problems that really solidify and bring out different aspects of the mathematical landscape. So to give an example of what I'm talking about, let's consider the following two arithmetical problems. So a student has learned addition, and we want to strengthen their understanding, give them something to do so they can practice, say, summing some numbers. So the first question is, calculate 1 plus 3 plus 7 plus 8 plus 14. And the second one is, calculate 1 plus 2 plus 4 plus 8 plus 16. Now on the surface, these are somewhat similar. The numbers are roughly comparable. But there is a big difference. The difference is that there is a very strong and obvious pattern here, while there is no really obvious pattern to the first one. The first question is sort of ad hoc. The only benefit in doing this problem is to gain some practice in addition. 1 plus 2 is 3. 3 plus 4 is 7. 7 plus 8 is 15. And 15 plus 16 is 31. When we're doing that, we very well may observe that there's something happening in this situation. That at every stage, the sum of the numbers that we've got happens to be one less than the next one. Like 1 plus 2 plus 4, that happens to be one less than 8. And 1 plus 2 plus 4 plus 8, that's 15, that happens to be less than 16 by 1. And the total sum is 31, that's one less than 32. So a student who does this question and is paying attention has the possibility of seeing this important pattern. What's important here is that each number in this sum is twice the previous one. And that, perhaps somewhat miraculously, the sum of all these things has a relatively simple, sort of almost like magical formula. You just take the next number in the sequence and one less than that. So our first puzzle is exactly the problem that we've already talked about. It's to show that if you take 1 plus 2 plus 4 plus 8 and you add 1, that you get 2 times 8, which is 16. Okay, and that's just one of a sequence of similar kinds of questions that you could ask. And so I'm just sort of giving you one version, but you could easily ask a more complicated or a simpler version. And because we've been approaching arithmetic in a very geometrical way, I remind you that our basic orientation to what a number really is a row rectangle, just a little rectangle of squares. Okay, that's sort of the elementary essence of what a number is for us. So I'm going to be concentrating on solutions, which are very geometrical in nature and that really accord with this geometrical understanding of numbers. I want us to have our students appreciate this and think in terms of the connection between arithmetic and geometry. Very much in the same way that the ancient Greeks did. Okay, so here is a geometrical solution for this question. We're thinking of these individual ingredients as numbers in the context of row rectangles. So here's 1, that's that 1 there in green. And there's 1, and there's 2, and there's 4, and there is 8. So we have to add up all of these things. That's what the left-hand side is asking us to do. And I'm going to do this geometrically. Okay, so what we can do is something that we could actually physically do if we actually had physical, like little plastic representations of these numbers, a little plastic rectangle with 4 adjacent squares there, for example. We could actually move them around. So that's what I'm going to do. I'm going to start with this thing here, and I'm going to copy it over there, and now I'm going to move things around. I'm going to take this green one, and I'm going to move it down here. Okay, so I'm moving it down there. I might do that in red. I have a red one around somewhere. Okay, so we're moving it in red, and then it's kind of gone, right? All right. So now we have this little combination of 1 and 1, and I'm going to move that down here now. Okay, so this little piece, so there was a blue one, and there was a green one. So I've moved that little couple down, and now it's no longer there. All right, now I'm going to take what we have here and I'm going to move it down there. So represents what we're getting, and we're going to move that down. So I guess there's a 1, 2, 3 blue ones and a green one at the end. Okay, so we've moved this little bar down there. It's no longer over here. And what is the total that we have at this point? Well, we see that we have 2 8s. there's now an 8 to go along with the original 8. So we have 2 times 8, which is 16. So going one more step, what we would want to do, perhaps if we wanted to find sort of one answer, would be to move this bar of 8 down again. I don't have room for it, but if you did, then obviously you're going to get a long rectangle, which is 16. So this represents a geometrical, physical way of rearranging things to make it somewhat obvious that you have a sum like this involving powers of 2 together with one additional one, that when you combine them this way, step by step, you're going to get the next power of 2. Okay? So having done this, you kind of see the pattern. It doesn't depend on the fact that we've just gone to this level. If we went down one more level or 2 more levels, the same pattern is going to work and the same thing is going to happen. So if you're explaining this to a child, it's great to actually do those different cases. Maybe start off with a simpler case. Maybe just start off with that sum and rearrange that sum to get 4. And then rearrange this sum to get 8. And then we've done this one, and maybe you could even go further depending on how many physical markers you've got. Now our second puzzle involves a very interesting family of numbers, historically very important, going back to the ancient Greeks, called triangular numbers. These are sort of special kinds of numbers. And here are the first 4. T1, T2, T3, and T4. And there's a kind of an obvious pattern to how they're formed. Let's have a look. So T1 is just a single square, which is our number 1. T2 is formed with a single square, and then below it, the number 2, expressed as a little rectangle with 2 blocks. So it's 1 plus 2. And of course that total is 3. So the second triangular number is 3. The third triangular number is 1 plus 2 plus 3. So maybe to make it a little bit clearer, I could sort of go like this. We're talking about a little rectangle in that direction. So there's a rectangle of size 2. There's a rectangle of size 3. If you like, there's a rectangle of size 1. So this is 1 plus 2 plus 3. We're just stacking the consecutive numbers together. A number is just a row rectangle for us, so we're just stacking them together to form a kind of a triangular shape. And then the number of squares in that shape is 6. That's our third triangular number. The fourth one, well, it's the same thing as we had before, but now we add one more row, and now a row of 4. So there's the thing we already had, and there is a new row of 4. And you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The total is 10. Okay, so we can explain to students what these little numbers are. And then the puzzle is to, first of all, find T5, T6, T7, and T8. So we're doing some arithmetic here. They get to practice some counting and arithmetic, but it's in the context of this very nice pattern, okay, which actually connects with lots of things and is historically very important. The next aspect of the puzzle is to show that 2 times T9, so after we've gotten to T8, the next one is T9, and this is sort of a way of getting at T9. It's saying that 2 times T9 is 9 times 10, which happens to be 90, but we write it as 9 times 10. And then once they've done that, then they can perhaps aspire to finding T10. All right, so let me give you a geometrical solution or some hints to solve this puzzle. So the first one is to find T5. So perhaps we could start by sort of picturing what T5 is. So there's the picture for T5. And hopefully we recognize that what this is what we obtained with T4, which is this one here. That's the T4. And then there's one more. Okay, so there's a T4, just outlined. And there's one more row. And the T4 was 10, and the row that we're adding to that has 5. So it's 10 plus 5 for a total of 15. So the fifth triangular number is 15. And you could get the students to carry on. The next one's going to be 15 plus 6. At some point you can dispense with writing down the pictures because they do get a little bit big. And just then the arithmetical aspect of the pattern should be clear. The next one you get by adding 6, then the following one by adding 7, then the following one by adding 8, and so on. Now for the second part of the problem, it asks to express 2 times t 9 as a product, 9 times 10. Here's the corresponding picture for a simpler version. Okay, so to illustrate the idea, we get students to think about simpler versions first, work out the simpler cases. Okay, and once we understand that pattern, then we can see how the same pattern is going to work with the bigger numbers. So 2 times t5. Well, here's t5 that we've just drawn, and 2 of them can be put together to form this larger rectangle. So I hope you can see 2 of these. The first one here is in red. Okay, the red one is just an exact copy of this thing, but colored red. And over here in green is also a copy of this thing, but it's kind of transposed. It's actually rotated. Okay, so instead of having the 1 up here and the 5 down there, it has the 1 down here and the 5 up there. Okay, so 1 plus 2 plus 3 plus 4 plus 5. There's another copy of T5. And these two fit together in this pleasant way to form a rectangle, whose dimensions are what? Well, 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5, 6. One more than 5. Because we have that top row of 5 and then one more. So the rectangle has altogether 5 times 6 entries, which is 30. And once you've seen this one and maybe done the T6 version of it, then the pattern should start being clear in the student's mind. They can say, aha, I can see why the same formula is going to work for the higher triangular numbers. So for example, 2 times T10 is going to be, in exactly the same way, a bigger rectangle with dimensions 10 by 11. So 2 times T10 is 10 times 11, which is 110. So what is T10? I mean, T10 sort of starts off by being the sum. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. We're adding up all of those numbers. That's a kind of a fun thing to do. And we've now just seen with this geometrical argument that there's a kind of a simpler way or an alternate way of finding what this big sum is without actually having to go through and add up all the individual constituents. How do we do that? We use the fact that 2 times t sub 10 is 110. So we're looking for a number so that twice that number is 110. Now we haven't done division yet, okay? So I don't want you to say this in terms of division, or at least not very formally. You can say, okay, we need to take half of 110. We've talked about half before, informally. What's half of 110? Well, half of 100, that's 50. Half of 10 is 5. And so maybe you can get the student to see that therefore half of 110 is going to be 55. 55 is the number, so that you multiply it by 2, you get 110. So that's giving us a kind of a magical way of adding all the numbers from 1 to 10 without actually having to do all that work. So this is a very rich example. It's a very important example mathematically. There's lots of sort of further ramifications of it and so on. But what we're doing is we're touching base with the sort of most elementary aspect here, getting students to manipulate small examples, seeing what the pattern is. Hopefully they can grasp that there's a pattern and they can predict what's going to happen from looking at smaller cases. So our third problem is a problem involving powers of 2 again, which we've already seen in the first problem. But now the orientation is different. So the problem is to use only the row rectangles 1, 2, 4, and 8. Just these ones. Each at most once to write each of the numbers 1, 2, 3, all the way up to 15. That means we have to take each of these numbers and express them just involving these 4 powers of 2. And we can only use any one of these at most once. And the second sort of part of this puzzle is, can you do this in 2 different ways for any of the numbers? Are there any numbers in here for which you can find 2 different ways of writing them as combinations of these 4 basic power of 2 tiles? Okay, so this is also connecting with all kinds of interesting things, binary representations of numbers and so on, but we don't have to really go into that story. We just want to present them with this challenge of playing around with these particular sort of tiles or rectangles and composing the other numbers in terms of them and seeing, is there another way of doing this, or is there just one way? So not all puzzles involve some clever arguments or computations. Sometimes a puzzle just involves in doing some interesting task. And that's the nature of this puzzle here, at least the first part of it. We're just trying to write all the numbers from 1 to 15 in terms of our 4 basic tiles. And here is the solution. And note, first of all, we're being systematic. We're starting with 1 and then 2 and then 3. Okay, so starting with the simple ones, systematically 1 by 1 by 1. That's a really good discipline to explain to young children. We want to go methodically, step by step, starting with the first ones. Okay, as there's 1 expressed in terms of our single tile. There's 2 expressed in terms of our single 2 tile. 3, we have to use the 1 tile and the 2 tile. That combination is equal to 3. And then you can check that the rest of these are hopefully correct. And also note that I've kind of organized them in a logical way. Not only have I listed them all in order, but in any one of them, for example, this one, I've written the solution with the smaller tile first. So here is 10 equals 2 plus 8. Okay? Writing it as 8 plus 2 is not really different. We're still using those same 2 tiles. It doesn't count as a different solution. It may look different, but it's actually the same ingredients adding up to get 10. And then it's maybe not entirely obvious, but the student can play around and see, is there any other way of creating 13 using these 4 tiles? And there isn't. Okay, for each one of these numbers, there's just one way, exactly one way of writing it as a combination of these basic binary tiles. And at this stage, it's enough for students just to play around and to say, look, I can't find any others. I can find these, but no more. And that's good enough. Okay, we don't need an abstract proof or anything like that. We're just at the level of observing what's actually happening and what we can do. This is a great puzzle. So our final puzzle is a little bit more open-ended, requires some sort of imagination, and we're asking students to verify a arithmetical relation, but entirely geometrically. So the first question is, show purely geometrically that 1 plus 1 plus 2 plus 2 plus 3 equals 5 plus 3 plus 1. Now, arithmetically, the way to do this would be to add up all these numbers on the left-hand side and separately add up all these numbers on the right-hand side, and hopefully those 2 numbers are the same. But we're asking here for a geometrical demonstration of that doesn't involve actually doing the arithmetic. And then the second question is sort of a similar thing, but a little bit more complicated. Show that in the same way, 1 plus 3 plus 3 plus 4 plus 5 plus 8 equals 6 plus 5 plus 5 plus 3 plus 2 plus 1 plus 1 plus 1. And once they figured out these things, make up your own version of this problem. And a somewhat more sophisticated question, how can we do this kind of thing without a picture? So this is kind of a lateral thinking kind of question, like an IQ test kind of thing, like what's the relationship between the numbers here and the numbers here? It's a great thing for a student to sort of struggle with and look at it from different points of view and say, what's really going on here? What's the relationship between these two sets of numbers? There is a very nice relationship. Okay, so this question is easier if it's done in the context of the previous questions where we've been working with numbers as row rectangles. Okay, if you don't have that sort of starting point, then it's maybe not so easy to figure out what's going on. But if you have that starting point, then you might very well say, okay, what's going on here with this, this left-hand side? 1 plus 1 plus 2 plus 2 plus 3. How are we going to think about that geometrically? Well, we're thinking about numbers as row rectangles. So there's 1, there's 1, and there's 2, and there's 2, and there's 3. So this represents this left-hand side as a sum of numbers as row rectangles. And once we've done that, then it's kind of obvious why this is going to be 5 plus 3 plus 1. Because when we look at it in terms of columns rather than rows, we see a column of 5 numbers, followed by a column of 3 numbers, followed by a column of 1 number. So those are numbers, but they're geometrically expressed as columns instead of rows, but as numbers, they're really the same. And so that's a geometrical understanding or demonstration of this inequality that doesn't actually require you to calculate the total. Okay, we don't know what the total is. That's not part of the solution. So once we have the hang of that, well, this is the same kind of story. The left-hand side, 1 plus 3 plus 3 plus 4 plus 5 plus 8. We're aligning all of these numbers so that they're sort of left justified. And then when we look at the corresponding columns, well, the biggest one comes first. So there's a 6, and then there's a 5, and there's another 5, and then there's a 3, a 2, a 1, a 1, and a 1. For the fourth part of the question, that maybe involves a little bit of thinking. So suppose we go back to the first question. 1 plus 1 plus 2 plus 2 plus 3. How could we write down the right-hand side without first drawing the picture? Well, after you've done a few of these, okay, then you might get the hang of it. What you should do is you should say, okay, of all these numbers here, how many of them are at least 1? There's 5 of them which are at least 1. How many of them are at least 2? There's this one, this one, this one. There's 3 of them which are at least 2. How many of them are at least 3? There's only 1 which is at least 3. How many of them are at least 4? Well, there's none of them, so further on. Okay? So that's a kind of a shorthand way of getting this thing that corresponds to this geometrical game with rows and columns, which doesn't actually require you to first construct the tableau, actually is the official name for such a thing, but doesn't actually require you to use the geometry. So these problems that we've presented today, these puzzles, all have an obvious geometrical aspect. We're trying to connect students' understanding of arithmetic with geometry. It's fun, so we're going to be doing some more puzzles in our next video, but we're going to move towards puzzles involving some measurement aspects. I hope you'll join me for that. I'm J Wildberger. Thanks for listening.